Okay, so this is joint work with Sue Avdas, who's a last year PhD student, and with Alin Tobescu and Daniel Xiang, who are working at Aptos Labs. So I'll start with some introduction about Aptos. It's a layer 1 blockchain, and a block of transactions is published every 1 second, and you achieve transaction finality in less than 1 second, meaning this is something I copied from my wallet. So I don't know if you can see here, it says the transaction was completed, moving money from one account to the other in 0.93 seconds. So this time it takes to go from my cell phone to the wallet of someone else, and it appears on the blockchain. So how is it done? There are more than 100 validator nodes all over the world, and they achieve consensus on blocks of transactions, which are published every about 1 second. And the power of these validators is decided by the token owner. So each token owner can decide to stake his or her tokens with any validator that they want. And a validator has as much power, relative power, based on how many tokens were staked with it. And the consensus assumes that corrupt validators own less than 1/3 of the total stake. So here's an example. So this is the state of the validators. I think it was 2-3 months ago. There were 129 validators spread all over the world. And actually each second they all collaborate to achieve consensus. And at that time, there were about 800 million tokens that were staked. And this is like from my wallet. I decided to stake 12 tokens with a validator called Beware Labs. Okay. So the amount of stake, the weight of that validator was increased by 12 tokens. And I'm getting like 77% rewards for this per year, and the validator also gets some rewards. And actually, I can change where I'm staking my tokens all the time. And the stake of the validators, the relative power changes all the time. And the way the system works is that you divide it to epochs, and every 2 hours is a new epoch, and validators might have new weight. Okay, so this is 2-3 months ago. There were 180 million tokens staked. And every 2 hours, this stake distribution changes, not by much, but it does change. And the validators, some of them had about 20 million tokens, the other had 1 million tokens. So they followed kind of this exponential decay curve. And you have to somehow do weighted computations, threshold computations based on this stake distribution, which always changes. Some other example that I couldn't resist showing because it just happened about 10 days ago on the network. And it shows like how fast we have to operate. So this is a tweet from one of our engineers saying, look what happened. The number of transactions per second increased from very little to about 2,000 transactions per second, which is about 100 million transactions per day. And they all appear on the chain, and the validators achieve consensus on all of them. So this is another tweet. Look, we're the blockchain with the most transactions per day. So what was the source for that? So it was a game, okay, a very simple game where you had to tap a cat. This is the cat, and if you tap it, it smiles, and then you get some reward based on how many times you tapped it. It went for 3 days, and each tap, it goes on chain, and the validators achieve consensus on it. Okay, so obviously, it's kind of funny. It doesn't scale, but it doesn't, probably doesn't pay for itself. Okay, but people are having fun, and also it shows the power of the blockchain, because you could have used this for other things like moving money from each person to another, and I think the number of taps we got here was more than the amount of transactions that Visa is processing. So you could have processed, this is a demonstration how the network can process this amount of taps. And something interesting, there is like one variable showing the total number of transactions, okay? And this is amazing because this is Sasha from our research lab. And what he tweets is like the amazing thing is one that we didn't fail. And also that we managed to keep this global counter because at each second there were 2,000 different taps and they all had to, in parallel, update a single variable. And the developers of this game, they don't know anything about parallel processing. The network let them do it. They did it in the background for them. So it's very good for parallel processing. So this is about the network. What we have to, we cannot slow it down. We have to be as fast as this is working. Okay. So we're generating randomness. And what is it good for? Okay. So games need randomness. Obviously, games where you throw dice, but also arcade games. Like apparently, kids really care to know that the way the games are used true randomness, and we heard this from different developers. They really care about the game being fair. And other types of game, Dragons and Dungeons, etc. You can think about randomized NFT minting, airdrops where you want to have like true randomness, transaction ordering to limit MEV opportunities. I mean, who knows? MEV is maximum extractable value is something which is worth a lot of money for decentralized finance. I won't go into it. You can use true randomness to choose leader for consensus, and I think it's also useful for zero knowledge proofs. So for zero knowledge proofs, we all know the Sigma protocols where the prover sends a commitment that then gets a challenge from verified, then sends a response. And we often use the Fiat-Shamir paradigm, where the challenge is a hash of the commitment. And if we assume that the hash is a random oracle, then this is secure. And most implementations use this paradigm because it doesn't need implementation. It doesn't need interaction. Now, the important thing is that the hash should have all the messages of the prover. And apparently this simple Fiat-Shamir paradigm, if you look in practice, people always get it wrong, okay? There are papers on finding weakness in Fiat-Shamir implementations. There are companies who do audits who the first thing they do is check for Fiat-Shamir problems. And the problem is that you don't put all of the messages from the prover inside the input to the hash function. It's very easy to get it wrong. It's amazing, for us as theoreticians, but once you look at the code, it always happens. So something you can do instead of using on-chain randomness, the prover could post a commitment to its first message on the block, then get on-chain randomness that was generated on that block after he posted the commitment, and use it as a challenge he uses to finish the Fiat-Shamir proofs. So this means that the proof will take 2 blocks, like to have to wait for a second, but you don't need interaction from the participants. And we are sure that the prover didn't know what is the challenge before posting the commitment on the block, because the challenge will come from another block. And so this reduces the amount of errors you can make. Also, it prevents the prover from doing a brute force search. So this means that the challenge could be smaller, say 20 bits or 30 bits, if it's good enough security for you. And if the challenge affects the length of the proof, then the proof might also be smaller. And I can talk about this offline later. Okay, so what we want to achieve for randomness, we want to achieve what we call verifiable random function, which is a function that has 2 properties. First, it's unpredictable, it's indistinguishable from random. And also it's verifiable, meaning that in the beginning, we post some public key, and each time we post an output of the function, people can verify that it was correctly implemented. Say that the output of a certain block is the function applied to the block number. Okay. So if you can see that it's correctly implemented, then no participant can bias the output. There's only one output possible for each input. Now, one constraint we had is, where do we want this randomness to appear? So for each block, you want new randomness. So we have like block 0, block 1, etc. And then block I. It needs randomness Ri. So one option is to reveal the randomness just before the block is run. So just before, a fraction of a second before they commit to the transactions that will be run on that block. That's not good because it's too soon. If someone sees the randomness before, it has a fraction of a second to decide whether to commit to a transaction or not. And if it's a game, he know what the dice will be, and he can win. And if it's something financial, they can make a lot of money from this, and then they will definitely do that. So before the block is not good. Another option is to reveal the randomness after the block. This is too late because it will slow things down. So what we have to do is reveal the randomness exactly during the block. So all the transactions are being sent to the network. Each second, the validators decide which transactions will appear in the next block. They order them. And just after they order the transactions, we reveal the randomness for this block. So this ensures that no one can commit to can see the randomness after seeing the randomness. Sorry. So we have to do it very fast because the entire block takes less than a second. Another thing you could use, there are services on the blockchain world that give you random workers. They give you random values. There is D1, which is run between 16 companies, and Chainlink has a randomness beacon. So basically, in each block, you connect to this beacon, and you can get a random value. And okay, then you don't have to implement anything yourself. So one issue is security and reliability. In terms of security, we don't really think D1 or Chainlink will try to leak random values beforehand. But in terms of reliability, we don't want to rely on them that if they fall, then our services will fall. In terms of usability, that's actually a big question, a big issue. So we want to get fresh randomness for each block. We have a block every 1 second. They provide fresh randomness every less than 1 second, every more than 1 second. Suppose they also operate at the 1 second frequency and we reduce our latency to 0.8 seconds, then they will be later than us. So there's no way to synchronize our blocks with them. These are different services. So getting randomness must be a two-step process. I somehow commit to my transaction in this block, and only after this block, this is when D1 is giving the random outputs, I can process the transaction. So writing a program will take 2 steps, and this will be much more complicated. That people, simple developers cannot use this. So what we want is that for each block, the validators decide on an ordered list of transactions for that block. Immediately afterwards, they generate randomness for that block. And then the transactions for that block, they use the randomness that was generated for that block. And it should be an easy API. Anyone could use this randomness and anyone can verify the output. And this is the API that we have. If you use, like the first function is public function bytes. You want to get n bytes of random values. This is the function. The second one is to get values of certain length, a list of values, etc. So just like a simple, any programming language, but this randomness is generated by the validators and it's unknown before the transactions are committed and ordered. And if you call for these functions several times, you get different values, and different programs will get different values for the same block, just by applying a hash function to the main seed we generate. Okay. So how do we do this? So we want this verifiable random function, which is unpredictable and verifiable. And the trust guarantee we'll have is that validators with less than 50% of the stake, having, say, less than 50% weight or stake, whatever we want to call it, will not be able to predict random values. I mean, yeah. Okay. So what we're going to do is that every epoch, 2 hours, the stake distribution might change because, in my wallet, I might, give 10 tokens to a certain validator. So every epoch, the validators run a distributed key generation process, a DKG, when they set up keys for this verifiable random function. And this is done every 2 hours, and we don't know in advance what will be the stake distribution. And then each validator receives shares based on how much stake it has in the new epoch. Then every second for every block, the validators together compute a verifiable random function, and less than 50% of the stake cannot know the output in advance. And this is typically done by computing a verifiable unpredictable function, VUF, which is basically a deterministic signature, which is unpredictable and is also verifiable, and then applying a random hash function to it. So this is how we do it, how everyone is doing it. So basically, computing a unique signature and applying a random hash. Yeah. Okay. So just to recap, every 2 hours, These are validators. They run a distributed key generation process, which give the validators of the new epoch, which might be different than the old ones, private keys based on the stake they have in the new epoch. And then every second, together they compute the VRF output. Now, one issue about stake, we're going to use secret sharing, okay? And we have 880 million tokens staked. We're not going to use 880 million shares. Okay, we do some rounding. So basically, we assign, say, a share for every B token, say, for 1 million tokens. And the way we assign shares, we basically divide how many tokens you have by, say, 1 million and round it up, okay? So rounding adds some errors. Basically, what can happen is that the validator might, when you round, the validator might lose or gain up to 1/2 of a share, because I had like 1.5 million tokens, and I got two, say I was rounded up, I got 2 shares. So I gained half a share that I shouldn't have gained. But you can actually analyze this. And so for 100 validators, this means that the difference will be up to 50 shares, and you can analyze it and actually show that it will be less than that, and in most cases, and analyze the accuracy that you get. In practice, we're going to use something like between 500 and 1,000 shares. Okay. So how would you like to do this, like initially? So initially, okay, we'll do how we generate the DKG. Each validator will share a secret, and the sum of the secrets will be the key that we're going to use. So what we can do is that each player validator runs Feldman's verifiable secret sharing, VSS, generates a polynomial of degree T. This is the threshold that you need to compute the secret. Broadcast G to the power of the coefficient of this polynomial. This is known for anyone who's seen this before, and if you haven't seen this before, it will be, I guess, hard to follow. And then sends to participant J the value of the polynomial evaluated in J. If a participant has more than 1 share, he'll get several shares. And then if a participant receives a share, he verifies by computing the exponent if he received a correct share or not by comparing with the coefficient of the exponents that he had. And if he thinks he didn't get the right share, then he complains. And at the end, we sum all the secrets, and that's the secret that we're going to use. So this has a few problems. One is this broadcast. So each validator has to broadcast order of the total number of shares, values. Broadcast is very costly, and we don't want each validator to broadcast a long message. Okay, so that's not good. Another thing which is not good is that if a validator received a wrong share or claims that he received the wrong share, he has to post a complaint. This means at that point, everyone has to stop and decide who to blame, the validator or the dealer. So this slows everything down. We really don't want this to happen. Okay, and suppose we've done this. The way we usually do it, we compute, say, the BLS signatures. So in the non-threshold case, the private key is X, the public key is G to the X, and the signature is the hash of the message raised to the power of X. And you can verify it using pairing. I will show how. In the threshold case, each participant broadcasts the hash of the message raised to the power of its own share, or maybe if he has a few shares, raised to the power of each one of these shares. And then you can you can verify this. You can verify each signature share using a pairing, and then you do interpolation of the exponent. So this also is not ideal. One is that the participant has to send a message for each share that it has. So if someone has 20 shares, it has to send 20 messages and do 20 computations. And another thing is that you need to gather a lot of signature shares. If it's like, say, 1,000 shares, you need to gather 500 signature shares to have more than 1/2 of 501 and do interpolation. This is quite costly because we want to have it more efficient. So here our construction. So to do the DKG, what we use, instead of simple verifiable secret sharing, we require 2 properties. One is that the construction is publicly verifiable. PVSS, meaning that everyone, once the dealer posts the VSS message, everyone can verify that this transcript of VSS is correct. So if the dealer sends the share of validator 1 encrypted with the key of validator 1, everyone can verify that this is correct, even though they cannot decrypt this share. So there's no need to start blaming. It's like you post a transcript, everyone can verify that it's okay. It's kind of tricky how to do it, but people have done it before. There are quite few constructions. Another property that we want that this PVSS is aggregatable, meaning that if I have a PVSS transcript from one validator, from one dealer, and from another dealer, I can combine them together to one PVSS transcript of the same length that will share the sum of the secrets, and also everyone can verify that publicly that this is a correct transcript. Okay, so we need these two properties. Currently, there's only one aggregatable PVSS construction that we know and is efficient due to Gurkhan et al. And we use some variant of it that we designed. And some caveat there, which is actually quite a headache, is that it doesn't share a field element. It doesn't share like a value A in ZP star. It shares a group element. It shares G to the A. So we have to compute a VUF which uses G to the A as the key, not A. Okay. So how do you implement the DKG? So the naive way would have been for each validator on the left to broadcast the transcript. Instead, what we do is that each validator sends the transcript, the PVSS transcript, to each other validator using peer-to-peer messages. Okay, this is much cheaper sending to others. They don't have to, like, the first recipient doesn't have to verify that the second recipient received the same thing. It could be a different thing, but each one of them has to be a correct PVSS transcript. So each one sends these transcripts in parallel. Then one of the recipients, one of the validators in the new epoch, once it receives correct PVSS transcripts from validators that has more than the threshold of the stake, he aggregates them to a single PVSS transcript and broadcasts it. So this means that we only broadcast a single message here by one of them. It could be that if the first validator is aggregating, he would aggregate a different final transcript than the second aggregated, but it doesn't matter. If more than the threshold of the validators are correct, this will be random. Okay, so we only broadcast a single PVSS transcript. So the way the system works, in the PVSS, you only broadcast a single transcript, which is great. Then each validator receives from this private keys based on its weight. And then every second for every block, they compute the VUFs. And the important thing here is that the contribution of each validator to computing the VUF is of constant size, independently of its weight. So if a validator has weight 20 or 50, its contribution to the VUF output will be the same. So the total number of contributions is the number of the validators, which is something less than 100. Okay. So before talking about the construction itself, how much time? 2 minutes. Okay. So I'll skip this. You know what? Actually, this is the most, it's not our construction, but it's important. Pairings are expensive, okay? Exponentiations are faster. Multi-exponentiations, doing multiplication of many exponentiations is much, much faster. This is what you want to do. If you replace n pairings with a single multi-exponentiation, you gain 2 orders of magnitude. Like, this is extremely important. Another thing, computation can be parallelized. Communication is more important because you cannot parallelize it. Okay, you can remember this. Now, let me show you I think I can show the construction. Okay, okay. So what happens is, so the secret key, no, I'm not able to use a pointer here. So the secret key is this h to the power of values of the polynomial that I get as much as my weight. So validator, the weight wi gets a key ski, which is, wi values in the exponent, this h. Now, the first thing that the validator does he chooses a random value Ri, and he publishes age of Ri, and each of its secret keys raised to the power of Ri. So if my weight is 20, I publish like 21 such values. Each of my private keys, which is scary to publish them, but raised to the power of a random exponent that only I know. So this is secure. And using pairings, you can verify that these values are correct, that I did. You know my public keys, you can verify that I published my secret keys raised to the same exponent. Okay. Now to compute the function, what I do, if I want to compute the function on M and I'm a validator, my signature share will be the hash of the message raised to the power of 1 over Ri. The Ri is the one I used earlier. Okay, so it's independent of my weight. And you can verify that I raised to the right power by pairing tricks. You can verify this. So this is how we find out the derivation we do. So we have like a subset T of validators that gave shares, each one of them just a single share. First, we verify all the shares using this pairing. So if you have like 30 shares, I do like 30 pairings to check this. Then I have these secret keys raised to the power of Ri. And there the validator provided the hash of the message raised to 1 over Ri. So if you take the two of them and do a pairing, it kind of cancels out the Ri, and what I get is the hash of age and the hash of the message raised to my share of the polynomial. And then this thing you can take from all the validators and do a interpolation of the exponent and compute the output. And then the math just works. So the main trick is publishing my private keys raised to the power of Ri, and then my signature share is the hash of the message to the power of 1 over Ri. So this I'll skip. The security reduction is based on the bilinear Diffie-Hellman assumption, meaning that if I have G to the A, G to the B, and G to the C, in both groups of the pairing, I cannot compute G to the power of A, B, C in the target group. This is a very, I think, common and conventional assumption in pairing-based cryptography. And security reduction is pretty straightforward. So just like last slide about performance. So our system is the pink one. Implementing BLS signatures is the other one, the white one. And like the 3 columns are for increasing number of shares. So you see that the signing time in our system is constant because you always do the same operation regardless of how many shares you have. Aggregation time is better, and the signature size is constant because it doesn't depend on how many, what's your weight. In terms of end-to-end performance, so the first 2 columns are how much time it takes to do the DKG, like every 2 hours. So it takes about 20 seconds for 800 shares. And the time it takes to generate on-chain randomness takes 160 milliseconds. However, if you take an optimistic path for the consensus, you can reduce this to 30 milliseconds, which this is what happens in practice. So 30 milliseconds out of a second is not bad as the additional delay we add. And that's it.